Screen share, sharing screen. Okay. Is it visible now?
Yes, Banshi.
Yes,
Yes.
Banshi.
Hmm. Today I picked the dielectric. I mean, from where it comes and its basic foundation. So, dielectric means we all know that this is Coulomb's law. Means force equal to Q1 Q2 by 4 pi epsilon r square. Okay, so this law is already there in the Maxwell's time, and Maxwell's quantified means electric and magnetic field together and give a theory for electromagnetic wave. And Maxwell actually did a means very huge contribution. Means whole electromagnetic world then comes in scientific research. Then, but for chemistry, for us, means how to apply those electrostatic interactions, or means mainly we are dealing with electrostatic interaction. Means magnetic things are there, but for us, electrodynamics is most important. So, means how do we deal with the electrostatic interaction for the material world? So that is basically, that means actually Lorentz 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 did a Lorentz put a lot of contribution there. Means without him we don't have means today we don't have such kind of nice experiment. Like now people are talking about dielectric, people are probing confinement effect in terms of dielectric, and although they are talking about means protein environment, means protein solvation in terms of dielectric. So means earlier, before Lorentz, it was there, means the fundamental law is there, means q1 q2 by 4 pi epsilon r square, this force between two charge. But in terms of microscopic, in the microscopic world, how do you think about that force? Because in the micro, means that force means there is a medium which screen that charges, so there is a reduced force that is scaled by epsilon. But for the microscopic case, if we think about some inhomogeneity in the material, so suppose protein water system, so protein surface has a inhomogeneity. Okay, and if there is a cavity, there is another inhomogeneous medium. So in that surface, means if we approximate this average dielectric constant, then this will not work. Means we cannot explain many experiments. Means protein response, we could not explain many things. So we have to think in terms of molecular terms. But in the time of Lorentz, that all those molecular structures are not so well established. So Lorentz actually came up with this. How do we get the means molecular dielectric constant? Means basically, how do you think microscopically of this interaction? So that is a huge contribution of Lorentz. But if we see the means only the Lorentz contribution, this is a small contribution from him in this direction. Means if we see the whole work of Lorentz, because he did that Lorentz contraction, means Lorentz transformation, for which actually Einstein could think about its special relativity. And also Lorentz actually got Nobel Prize due to this Zeeman effect, means splitting of magnetic field. Means Lorentz understood that means molecule is made up of electron and proton, and electron is rotating, so it has a magnetic field. So if we put external magnetic field, it will split, the energy level will split. So it is Zeeman effect, and his student Zeeman actually proved it, means his idea. So he got the Nobel Prize. And of course electromagnetic radiation, he has a lot of contribution. So we should give respect to Lorentz whenever we are studying dielectric. Means this is one main thing that I think that means we do not put proper respect. Means who is who discovered that thing, and for whom that whole field is generated basically. So means if we do not put proper respect, then means this is a negative reaction to us, means for which we could not think actually. So this is the our main motto, that how could we think microscopically, means when we have only that macroscopic formula in our hand at that time. So I will show two recent examples, means where this idea, means due to this Lorentz, where means till now those that very initial concept is still now useful for us. Means even if we have means very fine molecular structure, we have the knowledge of very fine molecular structure or very accurate molecular dynamic simulation, but we mean still this Lorentz model, whenever experimentalist or theoretician stuck somewhere to explain something, then they just recall Lorentz, how Lorentz think, and they just set around their problem. So they are, suppose this is a protein solvation. So protein solvation, there you can see that this local dielectric constant, okay, we can derive, and also this air water interface, this spectroscopic for the spectroscopic observation, this air water interface, air water at the interface, this is highly inhomogeneous, because from bulk phase it is going to the air phase, vapor phase, so liquid phase to vapor phase. So at the middle it has very strong inhomogeneity. Okay, so there we cannot think like a average out effect. Means we need to accurately describe the dielectric constant at the interface. Means dielectric constant, why do we need the dielectric constant at the interface? Because we need the local electric field. Okay, means why do we need the local electric field? Because this means from the local electric field, if we know the accurate local electric field, then only we can calculate the response from it. Okay, if we are assuming the electric field will be the same, whatever be the value whenever when it starts, means if we consider the electric field will remain same throughout its trajectory, then we get a different, we assume a different electric field at the interface, but reality is that electric field will change according to its local dielectric constant. So if we can know the accurate electric field at the interface, then only we can calculate the accurate response. Okay, so this kind of work is just recently published in PNAS in the last year, September, means very recent work. So that idea is, this Lorentz idea is means still very much useful and relevant in the in the field of material science. So if you have any questions or any discussion, if you want, so you can stop anywhere, you can stop me anywhere and we can discuss. Okay, is everything? Hello?
Yeah, you are audible.
Okay. So electric polarization means whenever there is an electric field in a medium, this is a epsilon naught E. means this is the electric field in the medium, and this is the polarization. It creates an induced charge or induced dipole in the system. So for this, there is a induced electric field, we can think. So this is the P, means polarization. So there is a total effect. What one is external electric field and one is induced electric field, means we call it means induced dipole or polarization. So this is the net effective electric field. We call it electric displacement. Okay, so then we can means this is just means we can write it in terms of means relative dielectric constant. So then we can write it in terms of susceptibility. Okay, so means epsilon relative dielectric constant equal to 1 plus susceptibility, means this kind of, these are the definition of relative dielectric constant and susceptibility. Okay, so in that time they have not accurate knowledge, but they understood those kind of things, that monopole, dipole, quadrupole, means what could be the interaction when there is a charge distribution. Okay, if we observe a charge distribution from very far, means when this r minus r prime is very large, then we see that there is a point charge. Okay, so there is just, we can use just Coulomb law. But when we approach towards this charge distribution, one can visualize all those distributed charges in the space. So their Coulomb's law is no longer valid. Means Coulomb's law is valid, but point charge based Coulomb law based on this point charge is no longer valid. So we have to take all those point charges, all those distributed charges, and take a sum of it to get the net potential, net electric potential. Okay, potential means gradient of potential means field. So this potential is sum of all those distributed charges. Okay, then we can expand this in terms of Taylor expansion. So there means there it is 1 by r, means it is important in the Taylor expansion. This has to be a convergent series, means when r is very large, then only it valid. Okay, if it is nearby, means very close to the charge distribution, then this Taylor expansion is not valid. Then we have to calculate exactly in terms of this, means there Ewald summation and all other discussion, that will be a long discussion and we could discuss it another time. But here we assume that r is somewhat larger, so that this series, Taylor expansion series, converge. So we can approximate it first order, second order, zeroth order, first order, second order term. So second order term is the dipole of that charge distribution and quadrupole of that charge distribution. So we can think like that, means when we approach very far away from that charge distribution, we see a monopole like of thing, and when we are little bit closer, then there is two positive negative charges visible in different way. Then when we come much closer, then with that monopole dipole, a quadrupole distribution is also visible to us in terms of in terms of the distance between this charge distribution and the observer, means all the terms are visible. Okay, so this is the dipole. From this expression we can find that this is the dipole is qi qn rn, means this first order term. This quadrupole is the second order term. Okay, so we can think in terms of means whenever we apply electric field, we can think in terms of dipole only. Okay, means it initially it has a dipole, and finally means whenever we apply some electric field in a charge distribution or in a material means there are negative and positive charge distributed somewhat means symmetrically or some inhomogeneous manner that we don't know. So there is a charge distribution inside a material. So if we apply an electric field, then there will be induced dipole moment, even if it is neutral at the beginning. So induced dipole moment, we can relate it in terms of electric field, means if electric field will be larger, then induced dipole moment will also larger. So we can relate it in terms of electric field, and this proportionality constant is the this coefficient is the polarizability, hyperpolarizability, and second order hyperpolarizability. Okay, so in terms of electric field, we can write the induced dipole moment. So induced dipole moment. So why we need induced means in this kind of formula? Because this alpha is the molecular property. This polarizability or this polarization, effect of polarization is captured in the alpha. Okay, so that's why this type of formula is useful for the molecular description. So Lorentz picked this kind of description and define the induced polarization is nothing but the means nothing but the dipole density at unit volume. So dipole density, we can write it in terms of polarizability, means this first order term he only take, means this is very, means this kind of strategy is very common, means whenever we try to solve analytically, means we want to have some guideline, okay, for our experiment or some theory. So we have to have some means analytical expression, means that will be a guideline for the simulation also. There are many conserved quantities, so that are guideline. So where this comes from, means if we take this square term, cubic term, then it will be more accurate. Then, but we could not solve it analytically. Okay, we have to go to again numerics. So we take this first order term, and this polarization depends on this rho means density, and this is molar mass. So this polarization depends on this polarizability and electric field. This polarizability is the molecular property. So Lorentz's main focus is to extract the polarizability. How to get the polarizability? So polarizability for that when there is a dielectric. Okay, so polarization in terms of relative permittivity, relative dielectric constant, whatever you call it. So this is means polarizability is related to this relative dielectric constant. Okay, just simple rearrangement of the equations, two definitions. So relative dielectric permittivity is easily measurable. So we get the polarization. Okay, but this is the average polarization. We have to average polarization means in between two capacitor, means whatever be the means there is a dielectric, but this polarization, if we calculate this relative dielectric permittivity, so this is the permittivity, relative permittivity of the whole system, means there is a interface and interface of the dielectric, and in between it will change. So Lorentz actually think about all those possibilities, means how to analytically take care of all the things to get the very local effect inside the dielectric. Means so this is Lorentz thought that this is the external electric field, and there is a dielectric, this is the dielectric material, and due to the induced effect, induced polarization, there is a additional electric field. Okay, means this is a positive to this is a negative to positive direction. So additional electric field will be in opposite direction. I will show later. But there is the additional electric field, on top of the external electric field. Okay, so this is called local electric field or additional electric field. And this total electric field, then total effect electric field inside the dielectric material. Means if we want to calculate the local electric field inside the dielectric material, then we have to consider both the external electric field plus this local electric field. Means without this local electric field, we could not understand. Means that would be erroneous. So Lorentz actually derived that local contribution is that induced contribution as P by 3 epsilon. Okay, means what is that average polarization? Means that by 3 epsilon naught. So by simple rearrangement, we can derive this famous Clausius-Moissotti equation. Okay, Clausius-Moissotti equation means relate this relative dielectric permittivity with the local polarizability. This is the microscopic property, and this is a macroscopic property, epsilon r. Epsilon r is not local, this is average, and alpha is the means very local property. So from macroscopic to microscopic, when we have no idea about the molecular structure, means how we can think, means to get some guideline or get some analytical solution. That is what Lorentz big contribution in that field.
Banshi,
Mm-hmm.
so when you call this additional electric field or say induced electric field or local electric field, so these are synonyms, right?
Those are synonyms. Additional or induced electric field. Those
or
are
local.
synonyms. Local electric.
Yes.
So how Lorentz derived that? Means this is my capacitor. If we look first on the right side, this is the capacitor. This is positive charge. One is positive plate, one is negative plate, and inside that there is dielectric. This is typical experimental setup. And due to that, they will induce a opposite charge, means this is negative and here is positive in the dielectric surface. Okay. Now inside the, if we go a local point, means inside the dielectric in microscopic point, around that we can think in terms of a sphere. Around that there is a induced polarization due to this charge separation. Because of negative charge there is a positive induction, and due to the positive charge there is a negative induction. So there is this is induced electric field, and one more electric field will be there. This is due to the local charge distribution. Okay, but that time Lorentz have no idea, means what is the accurate accurate atomic positions, accurate position of the atomic dipoles, or that accurate molecular structure. That time Lorentz do not have those information. So means they means it would be locally, he thought that it would be symmetric. Okay, means positive charge distributed over some negative charge, or negative charge distributed over some, like this kind of thing. So this due to this local charge distribution will be very small. So he approximated it to 0. Okay, this is a not very drastic error. This just a means marginal change will be there even if we include these kind of local things. And obviously, means when experiment, this is a baseline, means otherwise if we have, even if we include all those local distribution based on this experiment today, this neutron diffraction or very accurate ab initio simulation, then analytical solution we could not make any analytical solution. Means so to get
in this right hand figure, so why this positive pole is towards positive pole and negative pole towards negative pole?
This right side figure, this positive Now this is the
Yeah.
capacitor plate, means at very right figure.
Okay.
This is the
So
capacitor plate,
capacitor,
and
but
inside
then
that this is dielectric.
Yeah, Banshida.
Mm-hmm.
So in the figure number 2,
Mm-hmm.
so that one is also the induced polarization, correct?
Yes, yes.
And then again you are saying that inside that material also there is
Mm-hmm.
a local induced polarization happening.
Yes, yes,
Okay.
yes.
Yeah, Banchita,
Mm-hmm.
we can have more than one this local induced polarization in the system, right?
Yes.
So
Of course.
that will also affect each other.
Yes, means this is a, yes, that means that is exactly when your system is much more inhomogeneous, then there is different patches of means induced dipole that will affect each other. Okay, there is no similar kind of induction effect, just like protein solution. Okay, so there all the things are just means extension of this very basic idea. There you could have a analytical solution or could not, means depending upon the complexity of your description. Okay, but main point is that this is the basic thing, means basic first approximation where you get the exact analytical expression for this local effect.
Okay,
And
so
the same thing is used, the same description is used even today itself, when there is a, means just like I saw a paper that there is a interface, means interface we don't know, means what is the local dielectric constant, and means when I talk with experimentalist, they also have some, they also had borrow some approximated expression from Lorentz or some others following work, means, but we for due to that very inhomogeneous nature, we don't know what is the local dielectric constant, so we are we could not accurately derive the local electric field. Okay, so they are this kind of basic idea we must have, otherwise we are completely blind there what to do, means in the means in the bulk system it is okay, means there we have the, we can still work with these very homogeneous cases, we can still work with this epsilon, means relative permittivity, and we can borrow these some Lorentz correction and this, but whenever your system is complex, means inhomogeneous, just borrowing that expression will not help, means you have to know how Lorentz derived that, then only you can deal with these inhomogeneous cases, means that is the main point of discussing that, means uh, means means you can think in terms of complexity only when you know all the knowledge about this basic fundamental expression, means how it comes.
oh, okay, Banchita.
Okay.
Vanshida,
Mm-hmm.
some basic, I have some basic doubt. So this polarization is a phenomena,
Mm-hmm.
and the dipole constant we are talking about, it's the strength of how my system or my material is getting polarized. Correct?
Mm-hmm.
Is it correct?
Dipole, could you?
The dipole constant that we calculate
Dielectric
is
constant.
actually dielectric constant.
Mm-hmm.
That is
Dielectric
the
constant we measure.
intensity of my material is
Yes.
getting polarized.
Yes, yes, that is the from measurement that we can measure the relative dielectric constant.
Okay.
Okay, but this local means alpha means this means polarization. This is a microscopic property. Microscopic property means inside the dielectric material. Okay, where means inside in the microscopic scale how it respond with respect to some external electric field. So means we have a macroscopic description. From there Lorentz actually derive how we can get this microscopic response.
Okay, and can you quickly explain the inhomogeneity concept that you are saying?
Inhomogeneity means, okay, inhomogeneity I can.
You are differentiating between these two, no? That
Yes.
polarization.
Means,
yeah.
See that model, okay, this air water model, this air water, if we consider only water bulk system, okay, then we can consider, means we can still consider, means when your system is homogeneous, then you can assign a average on an average response, means on an average relative dielectric permittivity, okay, or dielectric constant. But whenever your system has inhomogeneity, like this protein surface or air water interface, there you don't know, means how much it would differ from this average value that you measured. Okay, so that local response, that for the local response you have to know that local dielectric constant. Okay, means your light is, suppose if we consider this experiment, this spectroscopy, surface spectroscopy, PSFG, means there some light is coming with some electric field, okay, and interact with the interface material and then give a response. Okay, but the electric field, we measure electric field at the beginning, okay, but at the interface it will change. Okay, so if we don't know what is the actual electric field when it interacting with the molecule, interfacial molecule, then we have a wrong description. We are assuming that there is a same electric field and it is interacting with that interfacial water. So this is a wrong description. So for accurate description is, we need to know the exact dielectric constant. If we can know the exact dielectric constant of the interfacial layer, then we can get the accurate electric field at the interface, and from there we can calculate the accurate response. Okay.
Okay, so right now you are focusing on the how to calculate this dipole constant, dielectric constant value at the interface.
Yes, means how do your local, means basic question is here that what is the local electric field, local induced electric field. You have an external electric field, and due to the dielectric material there is a induced effect. Okay.
Yes.
So what is this induced effect is the molecular property. Okay. So means if you get that induced effect, you can know about the molecule or vice versa.
Okay. Okay, sir. Okay. Sorry, Banshi, you can continue.
So this means Lorentz actually think in terms of like a continuous medium, means homogeneous medium. Okay, means inhomogeneity means on top of Lorentz model we have to add one layer of complexity. So here we discuss the Lorentz model, means homogeneous Lorentz model. So the electric field U1 is just scaled by, means this polarized, means electric field E1 is just, means electric field, external electric field plus the electric field due to the polarization. Polarization means inside that dielectric and the capacitor, it passes through a vacuum state. So here the polarization effect, here the electric field Lorentz approximated is, this is just scaled by this epsilon naught. Okay, just normal polarization, means vacuum propagation of electric field through the vacuum. Okay, so because inside the capacitor, and when electric field propagate from the capacitor to the dielectric material, inside that there is a vacuum. Okay, this is the, this is just scaled by epsilon naught, but it is with negative sign. This is plus, this is minus. Okay, electric field that is in that direction, and this is E2 is opposite direction. So E3 is 0 because cubic structure. This electric field due to this local structure of local rearrangement of this molecule, this local structure of this molecule, so that they assume as 0. Now this part is non-trivial, means inside that dielectric, even if it is homogeneous, means how did Lorentz think about it? Lorentz think about it as it is homogeneous. We can think like as a sphere, and in the sphere one side is positively induced and another side is negatively induced. So this is the sphere, and one side is positively induced, one side is negatively induced. Okay, so if the polarization is P, polarization, this is the polarization, P is the polarization. If polarization is P, so polarization means electric field density. Okay, so means if we know the area, if we polarization is P, so if we know the area along this polarization direction, so the dq means charge density, polarization means density of dipole, so dq means charge density is just P multiplied by area. Okay, means this is the density of the charge at this surface. Okay, means, and this is the, when we think in the direction of the polarization, then this is just P multiplied by this surface area. This is the charge at the surface. But when we think in terms of sphere, then we have to calculate the charges at the sphere surface, whole the sphere surface. So in the, not in the direction of this polarization vector, but in some tilted direction, in some theta direction, this is P cos theta into dA. So P is the vector. So along a tilted direction, along theta direction, so what is the component of the polarization? This is P cos theta and dA. This polarization has negative sign because these two have, means induced and net electric field has opposite sign, opposite direction. Okay, so this, we have to calculate this dA to calculate the charge at the sphere surface. So dA we can calculate. dA is, means dA is just a sphere, a spherical slab at the theta direction, means this is a strip from the sphere at theta direction. Theta means P direction is perpendicular and strip is taken at theta direction. So it is 2 pi. 2 means the surface, means when we calculate this dA, means we can calculate just like the surface area of a cylinder. Here it is not cylinder, it is like a portion of a sphere, but we can think like a sphere, means it is 2 pi r into h. So here it is also 2 pi pq into qr. Qr is like h. Okay, so if we replace this, pq means r sine theta, pq means this radius is r, means pq means r sine theta, and qr means r d theta if d theta is very small. So dA is 2 pi r square sine theta d theta. So here this dq means total electric field. This is dq. Okay, Yes, so total electric field equal to dq cos theta by r square. Okay, dq means p cos theta dA into cos theta by 4 pi r square. So we can integrate it out from 0 to pi, means over whole sphere, means theta will be integrated out from 0 to pi. So we can get this expression p by 3 epsilon. So it is a simple derivation. So I just stop here for discussion. It is just derivation, means.
Banshida,
Mhm.
so this is E4 is the one that you said it is equal to 0.
Sorry.
So you said in the earlier slide that this one is equal to 0. Due to
This one equal
cubic.
to 0. This E3.
Okay, so this is E3 and
This is E3.
okay,
Now we are calculating E4. E4 means around that material structure.
so the sphere you are taking is E4, and inside that sphere you are talking about the molecular structure, that is E3.
That is E3. Means this is not a bad approximation. Means we can select the collection of a molecule where this symmetric neutrality is maintained.
And inside this sphere, the yellow dot, that is the point A.
That is the point of interest. Means where
In the derivation, it is A.
yes, this is the point A. Yes, exactly.
So I'm
And
lost
there is
here.
a local
Actually,
structure inside the, means around
okay.
this A, local molecular structure. That
Ah.
structure is not contributing to the electric field, because we
Okay.
choose, or there is a very symmetric inherent structure. Due to this homogeneity, we can choose also. So this is 0, E3 is 0. Then only remaining field is E4 here. E4 means around there is a induced field. Due to this induction, this is the induced direction, induction direction. So one side is positive and one side is negative.
No, can you just connect it? How the inside structure, you are saying it is 0, then why we are taking the sphere around it and then
Yes,
calculating?
yes. I understand your question. This inside local structure due to the molecule. Okay. This local structure means this due to the local structure means due to this molecule, due to this means if we consider a cluster of molecule, let's say water. Okay.
Yes.
Water and ion means if we consider if we take a local structure of water, means due to the charge equality, charge distribution, symmetric charge due to this homogeneous nature, means this means the net electric field due to these charges are 0. But there is a means we can there is a layer, means outside that local structure we can think. And
okay, like a
there,
solvation shell.
yes, means this is not the solvation cell of that cluster, we can think. Means okay. We have some induced, we have induced electric field from the overall medium. So there we can think that extra those polarization P, how it affects this how it affects the total charge here.
Okay. And basically when you are integrating E4, so we will get E2.
Integrating E4, yes. Integrating E4 means overall whole the sphere. Means
okay,
we are
okay,
considering
total E4 we
a
are
sphere
getting.
element means dq cos theta by 4 pi r square. So
okay.
total means this is a simple integration and just.
So we calculated for one sphere and then we integrated for whole.
No, this is not only one sphere. This is for the sphere element.
Segment.
Sphere segment.
Okay. Okay, clear.
Here segment along theta direction. So this is for whole sphere. This is
Okay.
Banshida.
mhm.
So here basically E4 is generated due to the induced effect of E2, right?
Yes, yes,
Okay.
yes. Induced effect of E2.
Okay.
So we can here you can see that this E4 is P by 3 epsilon. Okay, this is the polarization. This is the net polarization that we can measure experimentally. Okay, so it is scaled by 1/3. Okay, so it is not, means I don't know whether I am thinking right or wrong, means it reminds me that this polarization is a vector and it is equally locally, if we think, it is equally contributing in 3 directions. So locally it is somehow divided, means the 3 factor, if we try to understand physically, and that could not be, that also means I have not think critically yet. This is one thought came in my mind, that how could we think this 3 factor, means local effect is scaled down by 3. Even if we think means it as a continuum. So total internal electric field is summation of all the 4 field. So total internal electric field is this external field plus local field. Okay. So this internal electric field is called the Lorentz field. So this is the main groundbreaking work, means in that dielectric, because without that we have no idea. Means in few slide next I will explain means why this idea is so important. We have no idea what is the local field, and then if we have no idea the local field, then we could not connect the response with the external field, means that we could not do.
Banshida, go back to slide number 10. Okay, so here you are only considering the integration upon theta, right? Not phi.
Oh,
So
phi is
just
already, yes, phi is already in the volume element, means 2 pi.
Okay.
2 pi is
Okay.
already there. Means in phi direction it is not changing anything. So only in theta direction, means there are only one polar direction, only theta direction, it only changes.
Yes.
And this part is clear, na? Anjali asked.
Yeah. It's very clear.
This part is, more clearly to say, you can think a local cluster, local microscopic cluster, okay, not the molecular cluster, molecular one, molecular ionic, or not just single ion, means he have no idea before Lorentz, means there is no idea what about the how to deal with the local structure. So for the first approximation, means it is the clever approximation that we choose local cluster such a way from the homogeneous medium that local cluster, that microscopic structure is neutral, okay, around that point of interest.
Yes.
Microscopic structure is neutral, and means outside that microscopic structure it is, means there is a continuum response, Okay, continuum response due to polarization P that we can measure. And due to that continuum response, what is the electric field here at that point?
Okay.
Okay, there is an external electric field E. Okay, and there is a response from the dielectric, average response is P. Okay, that local response means local electric field. To calculate the local electric field, they considered a cluster, and around that he approximated that this response is same as this average response. This means P.
Yes.
Okay, means this has to be done, otherwise we have no clue. And this approximation is not so bad, because means in homogeneous medium it is not so bad. Means if we have means very means like air water interface, like very complex inhomogeneous system, then this approximation might not be valid. But we have to have that idea, means how we deal with this homogeneous system. Then we can add like charged cluster, or depending upon the complexity. Okay, so some different response from different parts, just like in SLAM model. Okay, in SLAM model there is half sphere. Okay, some response come from there is a different response, and the upper side there is a different response. So we could not calculate like earlier, like I have shown that we cannot integrate it like with same P, same polarization effect. We have to integrate with different polarization effect, means half side others and half side others by other polarization. So means without the idea of Lorentz, means we cannot think this kind of means extended model. Means this is our main problem, means we could not think out of the box, out of the tradition. Means someone derive an expression, we just use that. Means we appreciate the expression that we used. We appreciate that paper where we borrow that expression, but we have to appreciate the original person, then only we can think out of that line. So this polarization is a means this is also done, means this thought along this extension Lorentz itself explored somewhat. Means here Lorentz considered a continuum medium. Okay, means no molecular structure. Okay, but in an experiment, means if we apply alternating current, means if we apply this frequency dependent electric field, okay, in that frequency dependent electric field, if we use very high frequency, then polarizability we get very low response, very low polarization. But if we use very low frequency, then if we use very low frequency, then we get very high polarization. What is the reason for that? Means it is not constant. This polarizability is frequency dependent. Means there is a DC current, means a constant electric field. But if we put alternating current, means like electromagnetic wave. Okay, this is also an example. Means if we apply alternating current with some frequency, this response depends on the frequency. How it means, how could we explain that? Means then we have to, means we could not explain it by this continuum medium, because continuum there is a only single response. Means we have to we have to go inside some details. We have to go little bit of molecular structure. So that is indeed the case. Means here this is the orientation polarization, and in the radio frequency region, and in the this is distortion polarization, and very high frequency ultraviolet frequency. This is the response due to the electronic polarization. Means they are electron only response. Due to this, if we change electric field, this is very much intuitive, and we already know it. Means from our BSc that if we change the direction of the electric field very fast, then the only electron could respond. But if we change the electric field very slowly, then molecule get time to, molecule means suppose water, if we think water has a dipole, and dipole get time to reorient. Means if we change, if we give some time to reorient them, but if we don't give that much time, very fast change of the direction of the electric field, like in ultraviolet region, ultraviolet frequency region, then only electron can change its sign, change its place. Molecule does not get time to reorient. So it is depends on this frequency due to its molecular structure. Okay, basically molecular dipole. So this experiment clearly shows that molecule consists of some dipole, not the continuum. Continuum is just a approximated thing. So polar molecule in an electric field. So if we consider polar molecule in an electric field, so what is the Boltzmann probability? Boltzmann probability of suppose that polar molecule has dipole moment mu. Okay, so mu E electric field. So and cos theta is the direction between the dipole moment and the electric field. So what is the probability of that orientation of that dipole? That is the Boltzmann probability, which is exponential function, exponential mu e cos theta by kt divided by integration of, divided by full in normalization. So average mu is mu multiplied by Boltzmann probability over the whole orientation. Like before, we are calculating average dipole for the whole sphere of orientation. Okay. So here we can calculate. This is very simple integration, exponential integration of exponential function normal. So average mu we can calculate it like that. This is cot hyperbolic function minus 1 by x. Okay. So but this is not easy to deal with cot hyperbolic function. So at high temperature we can approximate it with like that, this function. So basically at high temperature limit we have average mu equal to mu square E by 3 kt. Okay, and polarization orientation, this is the average dipole moment due to the, means if we consider, if we want to calculate the contribution of polarization due to this dipole orientation, we get this average dipole moment divided by volume. Okay, divided by molar volume. So this is the orientation, this is the contribution of this dipolar orientation to the polarization. So this is the extra part. Okay, we have to consider this part also if we work in that that low frequency region. Okay, so this is the contribution, orientation plus displacement. This is the orientation. This is the alpha. Alpha comes from the high frequency part. We can think means electronic displacement, and this comes from this low frequency part. This is the this is due to the molecular dipole orientation, we can say. So this electric field now we can we have to use this electric field, means not the external electric field. Electric field is still we have to use the local electric field, means to orient the molecule will feel that local electric field, not the external electric field. So we can use the expression of this internal electric field, which is E plus means scaled by 3, divided by 3, polarization divided by 3. This is the internal electric field. And if we use that electric field in this expression, so we get this Debye equation. Okay. So we can calculate this overall polarization of this system. Okay, we can measure this, and we can measure this relative dielectric constant for that medium. Okay, so if we plot this polarization with respect to relative dielectric constant means polarization we can measure means relative dielectric constant. Those are same kind of, means this is just different expression but same measurement. Okay, so if we can plot this relative dielectric constant, means this expression means molecular polarization, we can say is this is just nomenclature. Means if we plot this quantity with respect to temperature, 1 by temperature, so from the slope we can measure the dipole moment of molecular dipole moment of the microscopic dipole moment of that system, means who responds to the electric field. So from this measurement, actually we can directly access the molecular information, molecular structural information with the, means due to this equation only. Because means if we don't have this kind of guideline, we don't know how to get the molecular information from this system. Means this is just like blind man with a stick. Means we know that Debye equation, then only we can get we have that idea that we measure this relative dielectric permittivity or dielectric constant, and at different temperature, and if we plot it, we can extract from the slope also, we can, from the intercept we can extract this polarizability and electronic polarizability, and from the slope we can extract this dipole moment. So
this dipole moment means induced dipole moment.
No, here dipole moment means overall dipole moment, means net dipole moment, because in the, means it respond, means the overall dipole is oriented, means induced, means when there is neutral, system is neutral, there is, means suppose atomic system, okay, atomic gas, so there is no permanent dipole, so there is only electron will distort, but here this whole dipole reorient and align along the direction of the electric field. Okay, so here this polarization contains all the part, means this electronic displacement plus this orientation. Okay, from where this, means we have to think from where this polarization comes due to electron displacement plus reorientation of the molecule. Okay, now only induced effect we get in also, that can we also can measure in this kind of region where there is no orientation, polarization is possible, only induced effect is captured.
Okay,
so in this frequency region, in low frequency region, we get both the effect, electronic plus orientation. So their polarization inside the system, polarization of the system, that means it is due to the electronic displacement plus reorientation. Okay. So this is the this is the extension of Clausius-Mosot equation when we include that orientation of the molecular dipole. Here, interesting part is that without knowing the detailed, without knowing the any detailed molecular structure, we have a strategy to extract that molecular dipole. We get a strategy from that equation. We measure some macroscopic quantity with temperature. From there, we extract this dipole. Although it will deviate, but because of the approximation, not totally whole, no system is truly homogeneous, but that we can explain on top of that, how much it will deviate and how much inhomogeneity is there. Those kind of explanation we can add, but this is the baseline. Okay.
Sanchida, so here the plot you are talking about is between temperature and polarization.
Temperature and molecular polarization this expression we measure these.
Yes, you were talking about that the slope will give me alpha and the other slope will give me.
Slope will give mu and the intercept will give us.
Yeah, I'm just clearing it out that the plot is between temperature and molecular polarization.
1 by temperature versus this whole quantity.
And what is this para-electric polarization?
Dielectric.
Heading. Yeah.
Okay, para-electric means this molecular polarization due to molecular orientation, just like paramagnetic. Paramagnetic means when we apply a magnetic field, then the magnetic dipole will orient along this magnetic field. This is the paramagnet. So para-electric has same meaning. And dielectric means just electronic response, means just to separate to separately call these two different kinds of polarization.
Okay.
Now, another thing is that this polarization, we know that this is very much frequency dependent, and if we think it locally, here we can see that in the visible region, there is frequency increases means polarization also increases. This is not that this frequency polarizability decreases with the frequency. This is not the case always. If we see locally, in the visible region, it will increases. This is due to the this is due to the detailed molecular structure. Okay, there is different kind of vibration, and some vibration prefers. Some vibration has the nature. Some of them are natural vibration of this system. So this kind of here this is in the vibration region. So these kind of things appears when we apply electromagnetic field, means light wave, in the material to get the response and measure the response from it. This is a important topic nowadays for this to get the material property and to get to know the microscopic property. Microscopic property means structure and dynamics of the material. Means we are using the light wave. Okay, light wave means this electromagnetic wave. They are both electric and magnetic field are there. But for us, for chemist, we mostly interested in the electric. Means we do not consider this paramagnetic material. Here we consider only this normal dielectric material. So, and we want to know this electric field, which is oscillating electric field from the electromagnetic wave, and how it interacts with the material. Okay, so electric field is this oscillating electric field. This is the amplitude A, and this is amplitude A, and this is wave vector cos kx minus 2 pi nu t. Nu is the frequency. Okay. Previously, we know that this response depends on the frequency. Okay. So here we explicitly consider means how when an electromagnetic field means it propagates, it oscillates in time and space both. When this electromagnetic field interacts with the material, means what is the change of the polarization of the material, means what is the response from the material, means what is the electric field inside the material, local electric field that fluctuates. That we want to know, because many experiments like spectroscopy and many dielectric, also dielectric broadband spectroscopy, there we send and terahertz spectroscopy, there we send an electromagnetic wave which interact with the material. So there is an important question that time, and because of that kind of thinking, we already know that Lorentz could handle this problem also, means because Lorentz developed all those things, means continuum to a means permanent dipole with a permanent some molecular structure, some initial molecular structure assumption. So Lorentz could handle this problem also and could give a guideline for this kind of experiment with the light interacting with the material, which is a hot topic today itself. So this is what baseline Lorentz said. Lorentz, this is the famous theory called Lorentz classical theory, very long time ago, 1878. So there Lorentz means this is a means this molecule, Lorentz understood that this molecule is interacting with other molecule inside the material. Okay. And it has a natural vibration due to this kind of graph. He has that intuition. So it has a natural vibration due to that interaction. Okay. So this local point, this local point in the black color, this is connected. He assumed that this is connected with the simple harmonic oscillator. Okay, simple harmonic oscillator means those are the interaction from the surroundings. Okay, and in presence of the electromagnetic field, okay, this means this electromagnetic field coupled with that oscillator. Okay, so what is the equations of motion for this in presence of an external electric field? What is the equation of motion for this point of interest, means black point? So when we apply a force and a particle is connected with a oscillator, okay, oscillator is providing a friction to that force. Okay, it will not move in that, it will oppose its velocity. Friction means it opposes its velocity. So friction actually coupled with the velocity term. Okay, so oscillator means external oscillator, means E, we can consider it E local, means local electric field, E local. Okay, and this E into E local, this is the net force. Okay, this electric field multiplied by charge, this is the net force we can think, and this is the, in the right hand side, this is the force, and the left hand side, what is the force that this black point interest, that black point experienced. So this is m multiplied by acceleration d2r dt2. Okay, this is acceleration plus this frictional force. Frictional force means friction multiplied by velocity. This is frictional force. Okay, and he modeled it. It is connected with a oscillator. So it has a frequency. Here it is a single oscillator for this equation, but he itself extend with the multiple oscillator. For first derivation, we consider here it is connected with a single oscillator, so whose vibration is omega t. Okay, this is the natural vibration of the oscillator of that model. Okay, so here this can be this can be solved. So this equation, this is a Langevin equation. Okay, Langevin equation is already there at that time. And what Lorentz did in the Langevin equation, we have a dragging force or friction force, and we have an external force. Okay, so we can write the equation of motion in terms of external force and dragging force. This is the Langevin equation. So Lorentz used that Langevin equation to calculate this, calculate the response of this point of interest inside the dielectric material. Here the external force is coming from the external electric field. Okay, so if we can solve this R, so mu equal to, means dipole equal to charge multiplied by distance. Okay, how R fluctuate? If we multiplied it by charge, then we get mu. And polarization is nothing but this average mu per unit volume. Okay, and then we can connect, if we can calculate this mu in some approximated way, just like Lorentz did, then we can get an approximate expression for this molecular polarizability or susceptibility or dielectric response or dielectric constant. So this is the expression, this is the steps, and I will show some key step for that derivation. Means this is the master equation. This is the Langevin equation for the movement of R, movement of this point of interest. Okay, so from this Langevin equation, we can calculate this R. We can solve it for R. Okay, for the displacement, and if we know the displacement, we can calculate this by multiplying the charge, electric charge. We can calculate this dipole. Okay, from this dipole we can get this dielectric constant. So this is the key step. So if anyone have any question here in the model, about the model or this key step, then we can discuss here. This is just free, means you don't have to think that means if we discuss any means any beginners types question, then what others think, that kind of thing. Means I might also, there is a probability that I might also explain wrong things. Means then you could also correct me. Means this kind of thing also. So it is totally internal. Means,
So this E-local,
mm-hmm.
is this electric field strength not equal to the external field strength that you have applied?
Local, for this model, he used this E-local for this derivation, and later we saw that with different in the derivation. Yes, in the derivation here this E-local means he took that actual electromagnetic field from the light.
Yeah.
With
So in case where we, in simulation that we do,
So we don't actually apply an electric field. So if there is no external electric field or applied electric field, then there will be no friction as well, right?
Yes, there is no friction as well. In simulation, we have to remember that we are not applying any electric field and not creating any non-equilibrium situation. There we assume this non-equilibrium thing to an equilibrium thing by linear response theory. Means if the electric field is very means if this external perturbation can be approximated, if the response due to an external perturbation can be approximated in a linear manner, then we can for this external response we can write down an expression for an equilibrium correlation function. Okay, so in linear response regime, there we need not have to consider any friction or any external electric field because of this linear response regime. Means their main assumption is the linear response. That is another topic of discussion that is also in my mind, that to connect means our calculation, what we are doing in terms of linear response. So means what is the connect, means how the means linearity simplifies our life. So that is another. But here, that time, linear response is not there. Okay, means it is also plus point that's why he forced to think that kind of nice model system, or where we can exactly solve the equations of the of the dipole fluctuations. Okay, equations of the dipole fluctuation means equations of the fluctuation of the displacement of that point. Okay. So Langevin equation is already there. Langevin equation is already there. So if we have means then for the Lorentz, the problem is that means if we write down the problem is that we have an external field, okay, and we have a friction due to medium, and this point is connected to a vibration, means connected to environment with some frequency, with harmonic oscillator, means like harmonic oscillator. Then what would be the equation for this for the fluctuation of this displacement? What is the equation for this displacement, evolution of this displacement? So that Langevin already means available. The Langevin equation is already available that time. So Lorentz is a known problem for knowledge. Just he has to model that thing, that there is a friction and it is connected to a harmonic oscillator. Harmonic oscillator comes means any analytical expression, means whatever I have seen come across, and I heard from other scientists, means like Professor Bagchi and all those things. They frequently talk about harmonic oscillator. Harmonic oscillator means if they want to get some analytical expression, just model it with some harmonic oscillator, and means bath is already modeled. Otherwise, means you can numerically you can get bath in the simulation, but analytically, if we want to have the effect of surroundings, we can approximate it by one harmonic oscillator. If it does not match, then two harmonic oscillator, like that, this bath effect. So that kind of things now people are still using, and still it is useful. So okay. Any more comments, discussion, or
No, you can continue.
okay? Here you can see that these. Yes, I came that slide. So better to explain here. So this is the equation, okay, Lagrange equation for that model system. That model system is made by Lorentz for that specific problem of this displacement of charge due to this electromagnetic wave. Electromagnetic wave means E naught e to the power I omega t. This is the electromagnetic wave. So the exponential here we can solve it by using a trial solution. Okay, y equal to y naught e to the power I omega t. So this just comes into a quadratic expression and we can solve it. So y0, we can get y0. If I put here, we can get y0, expression of y0. So mu equal to q into y. Okay, q into y. So q square e naught. So we put the expression of y, y naught exponential I omega t. So q square e naught m omega. So same, we can substitute the expression for y0, y naught. So this is the mu, okay, and if induced polarization is the average mu, okay, n mu. So from here we can get the susceptibility also. Okay, means once we have the expression for mu, then we can play with all the things, means susceptibility, dielectric, relative dielectric constant. Means the key quantity is the mu. Mu means in terms of Lorentz model, key quantity is the displacement. Okay, displacement of charge. This charge is connected to a spring, harmonic spring, and due to the path, it has a friction. So key quantity is the mu, means displacement here in that model. So
Bansida, just I have a doubt. This Lorentz classical theory, this is a master equation. So R is the coordinate, right?
R is the yes, displacement.
Basically, it's a vector
of this point of interest inside the dielectric.
Okay, so this has a frequency dependence.
Yes, this has a frequency. Yes, here R is depends on frequency. Here frequency
means like that physical significance I'm just missing out here. Can you explain it again to me?
Physical significance of these equations or these expression, final expression.
R is the frequency dependence. Frequency dependence of R.
Displacement is the frequency dependence.
Yeah.
Why it is so? Means in physically.
Yeah.
Physically, why displacement has to be frequency dependent?
Yes, and it's also it will also be a if we take this friction component, so it is a complex quantity according to the expression.
Exactly.
Yeah, that one I actually missing.
Yes, it is a friction. Friction comes with a complex.
Means so basically we will solve this differential equation. So it will come this complex quantity.
Yes, here naturally it will come.
Here.
So your question is that, means can we think the frequency dependence of mu physically? Is it your question? Frequency dependence of R physically?
This R is frequency dependence.
R means here Y.
Means,
Y is frequency.
So how it is changing with respect to frequency?
It is like we take an explicit example, water. Okay, water is connected with the surroundings, and we know that there is a intermolecular vibration, intramolecular vibration.
Yeah.
Okay,
yes.
And we are focusing in some frequency, terahertz frequency region. Let's say, means intermolecular water is connected with other water with some frequency omega. So this displacement of that center of this dipole of your interest, this is connected with that frequency for this intermolecular vibration. Okay.
Okay.
So that's why you need a harmonic oscillator connection for that central for that point of your interest. Okay, dipole of your interest.
Okay.
Okay.
Yeah.
So here we have this expression. Okay, mu equal to charge multiplied by displacement. Okay, charge multiplied by this. So from this expression, mu equal to alpha into E. Okay, so alpha equal to, so polarizability. We can get polarizability here. This part is the polarizability, and also we can get the, once we have mu, we can derive all those property from this equation: polarizability, susceptibility, and if we write down this susceptibility, okay, this n is square by epsilon naught n. This is the frequency if there is no surroundings, there is only the charge is separated, the E charge is separated, and then what is the response we get? N is square by epsilon naught m. This is the total, means what is the, means then charge, then there is nothing to against the charge displacement. So this is called plasma. For the plasma case, plasma, there is no bound state. Okay, all electron and proton, all are not bound to each other due to very high kinetic energy or so. So plasma is visible in some in the sun. Our sun is hypothesized that it is made of plasma, and means our Earth is very cool state, means they are all are bound state, but in the universe, most of the stars and all others species in the galaxy that are plasma. So okay, that is a different story. But here, this n square by epsilon naught m, this is the free response from this free electron. So we can call it as omega p, means plasma frequency. Okay. So this is just means nothing. I just gave the explanation for this notation, means, but in derivation, this kind of explanation is not required. So this dielectric frequency dependent dielectric permittivity is 1 plus susceptibility and 1 plus this. So when omega, we have two limit at
Vanshida,
okay.
can we continue for the next time?
Yes, I have two slides. Just derivation. I think I don't have to explain it in detail. Okay, I had in mind up to that part. Two
Okay.
slides more.
Okay.
So if omega tends to 0, then it is static dielectric constant, and if omega tends to infinity, then it is then very high frequency dielectric constant, omega epsilon infinity. So we can write dielectric permittivity in terms of infinite limit and static limit. So, and this expression is still used for this all dielectric measurement, means with such simple model system derivation, means long time ago, but this expression is still used, means for the experimentalist and even for the theoreticians, means they just model it by, here he model with single oscillator, there they model with multiple oscillator. Okay. So, and here we can see that this is the resonance appears when omega equal to omega naught. and this multiple oscillator model. Multiple oscillator model means they used different oscillators with different natural frequency. Okay, and then the dielectric constant will be sum of the response from all those oscillators. Okay, just extension means extension, straightforward extension on top of that. Now, last thing I want to talk about refractive index, because experimentalists often measure refractive index, and refractive index is connected to the dielectric constant like that. Means from the Maxwell's equation, we can get this refractive index equal to root over of dielectric permittivity and magnetic permittivity. But we are not considering ferromagnetic material, so we can only take the dielectric permittivity. So dielectric permittivity, then n square equal to exactly means what we derive for the relative permittivity, dielectric permittivity. So what is the n? From n square means here is a trick, means from we know the n square, n is a complex quantity. We know the n square. So how do we get the n? So this is not straightforward, but when for the gaseous medium, we can take the approximation. This is why this is not straightforward, because n square, complex square, this is not absolute square. Complex square means there is a coupled term, real and imaginary. So this is not straightforward. So, but when n near equal to 1, then we can approximate n near equal to 1 means this susceptibility is very small. Okay, n near equal to 1 means. So when this xc is very small, chi is very small, then we can expand it. We can expand it with infinite series, because this is a convergent series. So we can take the first term 1 plus half chi. So from there we can get this kind of simplification, n square minus 1 equal to 2n, so on. Then we can separate it in terms of real and imaginary part. Okay. So with that approximation in close to 1. So here we have we can calculate the real refractive index and imaginary refractive index. Why are we interested in real and imaginary refractive index? See, means we have this refraction, reflection, all those things, absorption due to light, means there are Lambert-Beer's law, and means people are studying refraction and scattering of light. People are measuring those things and characterizing the material based on those things. So their refractive index play a major role in the absorption and scattering. So this is consider this expression of the electric field of light. This E equal to amplitude into exponential I omega t minus kx. K is the wave vector. Okay, and this is my last slide. And k is my wave vector. Okay, wave vector is related to the, means this wave vector is wave vector inside the medium, propagation inside the medium, when light is propagating inside the medium. And this k is related to k0 by n. K0 means when light is propagating, wave vector when light is propagating in the vacuum, throughout the vacuum. So k equal to n k0, means this can be directly derived from this means n equal to refractive index equal to velocity of light at vacuum by velocity of light at that medium. So from there, wave vector has inverse relationship with this velocity. So k equal to n k0. Okay, so if we put that n k0 here, and n has two parts, one has real and one has imaginary. So n can be expressed in this way. Okay, real and imaginary. So we can separately write the imaginary part here, and this is the real component sitting there. Okay, and this is the this we can take it out. This I means I multiplied by I means -1. So this factor can be taken out from the imaginary part. So this part is the amplitude. We can, if we compare this expression with this last expression, and this part we can think a damped amplitude. Okay, amplitude that is exponentially damped. Okay, and this part we can think in terms of means change in phase with respect to the vacuum. Okay, so there is two different means real and imaginary part of the refractive index has two different influence. Means one is that imaginary component damped the wave, means that's why imaginary part of the refractive index connected to the absorption. Means if we measure the imaginary refractive index frequency dependent, then we get this absorption band of that system, and this real part is dispersion. Dispersion means scattering and means any kind of phase change of this in this propagation. So this part is connected to the real part of the refractive index is connected to the change of the phase or dispersion of the light in the medium. So but they are connected by means by Kramer-Skonnick relationship. This is other topic of discussion, but those two have different significance. Means real and imaginary part of the refractive index. Real part means this is scattering or dispersion, and imaginary part means absorption of the wave. That's why means this is the physical origin, means how this real part means imaginary part means absorption. Imaginary part has this expression. Okay, so when omega naught equal to omega, means when omega matches with this natural frequency, natural harmonic frequency inside that system, then there is this in this imaginary part magnifies. Okay, so we get a peak in the absorption band. Okay, so and this part has not peak. This real part, this dispersion part at this resonance frequency, it changes its sign at this resonance frequency. So that's how they connected with the absorption and dispersion. Okay, this is how Lorentz derives this absorption and dispersion with in terms of simple model, means where the central dipole or central point of interest is connected to some simple harmonic oscillator, and there is a friction due to surroundings. So by two inputs, he derived this microscopic expression, means with these two simple assumption. Means here one more physical insight is that this gamma is the friction. It depends on actually governs the line width. Means how much friction, means larger friction means larger line width. This is a Lorentzian function, so line width depend to proportional to gamma. So this larger friction means larger environment, mean liquid state. If we compare gas state spectroscopy with the liquid state spectroscopy, liquid state means higher friction, means higher connection with the surroundings. So we have this larger line. The gas spectroscopy has very broad band, as liquid state spectroscopy has very broad band as compared to the gas state spectroscopy. So with that simple model, we have this macroscopic expression and macroscopic understanding, means of our absorption and of our absorption and diffraction. So all thanks, I think we should give all the thanks to Lawrence. Due to him, we can think simple. We can think in very simple way. We can learn how to think very simple way, even for very critical problem. Means we have no pre-understanding of the molecular structure. We have some experimental microscopic measurement, macroscopic measurement. From there, we have to explain the things, why this is happening, connected to the Maxwell equation. Maxwell equation are there, and measurement on the material are there. But in between that, how to bridge this experiment and Maxwell's equation, that is done by Lawrence. Means that mostly means other people are there, but what we discussed today, there most of the contribution comes from the Lawrence. So without that, there is no further progress in this field of chemistry or material science. So we should give respect. Means whenever we are studying any dielectric constant or some kind of thing, we should remember the contribution of Lawrence, and we should have always a respect for him. For this, we have some kind of back reaction, so that we can think this kind of simple way, model system way to think a non-traditional way. Okay, that's what. Hello.
Yes,
So
Banshi,
in
yes.
the last slide, like 22 most probably, yeah, so this EY electric field, is it like perpendicular to the wave vector? Is there some relation, or I mean, I don't know, like EY?
This wave vector is in along x direction.
Mhm.
Okay, so electric field will be along y direction. Means propagation is perpendicular to the electric field vector. Propagation of light is perpendicular to the electric field vector.
Okay.
Okay, any comment, any suggestions, or any, even if it is basic, so we can discuss. Means from discussion we can learn many things. Means discussion is necessary for all of us. If anything is not
Banshi,
clear, I will-
just one thing, like in the first slide, you wrote that the Nobel Prize of 1902 awarded to Lawrence. I think that's not no.
I copied it.
Awarded at 1902 awarded to Emil Fischer. Right?
1902, I copied it from internet. Don't know.
1902 awarded to Emil Fischer, so that I
Fischer.
remember. That
No, he might be Nobel Prize in Physics.
okay, that can happen.
Right. Because this kind of work is Fischer means organic chemistry.
Organic Fischer.
Okay. That then it would be for physics.
Physics, I guess.
Vanshida, go to slide 18.
18.
Okay, 17. Yeah, so here you said that the displacement will give me mu, and after I get the mu, I can calculate epsilon. But in epsilon expression, from where the connectivity is there, because I can't see the.
Yes. Here I saw the key steps, and
Okay.
means from epsilon, you can see that means mu is connected with the polarization. Okay.
Mhm.
Here is the key step here. Mu is connected with the polarization. So we can get polarizability and susceptibility, and
Okay.
epsilon is 1 plus susceptibility, means once we get the mu is the key quantity. So all these defined quantity, those are just straightforward.
Okay. Yeah, that's it.
Yeah. Any slides is unclear, maybe. Whatever is unclear means it is better to stop there. So we can.
Yeah, Banshi.
Ankita, it's better if you share the slides in the WhatsApp group.
Yeah, that I can also do. I will also do.
And you may stop recording now. Banshi.
Yeah, means all those discussion is over, means probably.
Yeah, if there are no scientific questions.
Okay. Stop sharing.
No, recording, I mean.
Recording, pause recording, or how to do? Stop recording or pause?
Yeah, stop recording.
Now there is two options. I just first time, that's why I confirm.
Yeah, so pause means you will pause, but stop, now you can stop.
Okay.